Hello everyone, I'm Yuri Kostukevich, Assistant Professor of Skolkovo Institute of Science and Technology, and this is the second part of a tutorial dedicated to PyFragMS software that we are developing in our laboratory. In the previous part I was talking about area of research, I was talking about why we are developing new software, what kind of problems it can solve, and now in this part I will show you how it works. First of all, how to find it. You can Google our laboratory, Skoltech Mass Spec Lab, this URL address, and here in downloads you can find PyFragMS. Here on this page you will find a little description of this software, graphical abstract, some description, how it was created, and working link to PyFragMS software. It's here. This software was developed using Python and Anvil. Front end for web application was developed using Anvil. So let's go to PyFragMS and see how it works and what it can do. This software consists of three blocks. First block is database block. The second block is block dedicated to calculation of fragmentation trees, and the third block dedicated to the MSMS search using information of the position of isotope labels in MSMS spectrum. So let's start. Let's start with the first block, database. Here we have created and published a database containing. Now this database contains almost 7,000 compounds for which we have annotated MSMS spectra, and for almost 1,000 compounds we have MSMS spectra after isotope exchange reaction, after hydrogen deuterium exchange reaction, and for around 100 molecules MSMS spectra after oxygen exchange reaction. So let's find some sample molecule, for example this one, and we can choose polarity and for example spectra for MSMS spectra after hydrogen deuterium exchange reaction. Of course we have MSMS spectra for precursor molecular. This is the structure of this molecular. This is the precursor ion, MOVZ of precursor ion, and this is just a normal spectra for this molecular. And if we perform hydrogen deuterium exchange, in this case this molecule does not have labile hydrogens, but in positive electrospray mode the hydrogen attached during ionization will be labile, and it can be replaced for deuterium, and the mass will be 277. So we and this is a spectrum. So you can see deuterium in precursor ion, and you can see the inclusion of the deuterium label in fragmentation spectra. So you see that only in MOVZ 234 deuterium was included. In other peaks deuterium was not included, but this is experimental data. And also we have recorded spectra for C13 for C13 isotopes. You can pay attention to the peak splitting here. So this is a spectra for precursor ion. Of course, we have spectra for this molecule. We have spectra not only after hydrogen deuterium exchange reaction, but also spectra for oxygen exchange spectra after oxygen exchange reaction. In this case, this molecule has one labile oxygen, this one, and we performed oxygen exchange reaction. We obtained this molecule and recorded MSMS spectrum for this molecule. So you see smiles showing the position of oxygen label in a molecule, and you can see the inclusion of oxygen label in fragment spectrum. MSMS spectrum here is recorded in the following format: accurate mass, then space, intensity, space, and molecular formula. So this is a database. For simplification of the search for compounds, it is possible to use filters. It is shown here how to use it. For example, we would like to select only compounds from specific mass range. In this case, we should write such an expression. For example, we would like to select molecules with mass from 200 to say 210, and we should press this button to apply this filter. And in this case, you can see here only those molecules with MOZ in this range will be selected. For example, if we make it a little bit more narrow, it's also should become narrow. Yeah, so you see, and once again we can see what kind of spectra we have here. Yeah, so this is the molecular, and here we have spectra for precursor ion, unmodified, and spectra for this molecular after hydrogen deuterium exchange. Database is created by combining public data. Those are, of course, data published in MetFrag paper. Some of data were recorded by us. All spectra, all oxygen 18 exchange spectra recorded by us. And for hydrogen deuterium exchange experiments, some data were obtained by us, and some data were taken from MetFrag. Also, we included here all possible public databases in unsorted. Here there are many molecules. Yeah, here many molecules, they are unsorted, but it's also possible to use them. Okay, so also there are some filters. There are filters that could be used to find molecules by name. For example, if we would like to search for molecules containing say this string in name, we should write it like here, and you can we will find only molecules with such a string in a name. It is also possible to use to search for molecules with a specific number of labile hydrogens and labile oxygens using following notation. For example, now we will select only molecules with exactly one labile hydrogen. So yeah, you see only one labile hydrogen. It is also possible to use a combination of different filters. So, for example, this will select only molecules with exactly one labile hydrogens and with mass in this range. Yeah, so you see what was selected. Looks like it's for negative. Yeah, it's negative ions. So you see how it works. Mass is for neutral molecule, not for ion, for neutral molecule. So this is a database. I have shown you how to search this database using filters, and how to find some molecules in this database. So you see. Okay, now let's move to the second part of PyFragMS. The second part is instruments for creating fragmentation trees. What are fragmentation trees? Fragmentation tree is a directed graph that carries information of the fragmentation pathways. Let me show you. Let me show you. Yeah, here. For example, if we have some molecules that is fragmented in a collisional cell, and we know that fragmentation is a stepwise process. First, molecule accumulate internal energy fragments, and then these fragment ions, they can further fragment to produce MSN actually ions, but since we are recording, since we cannot remove such ions from interfaces of ion optics, we are recording all of them, and in this mass spectrum which we are recording, we do not know which ions corresponds to which number of fragmentations. And fragmentation tree is a direct graph that carries information of such consecutive fragmentation. So initially we had this molecular, and fragmentation tree shows how this molecular is fragmented to eventually produce MSMS spectrum, which we are observing in our experiment. So this is fragmentation tree, and PyFragMS is a software for creating such fragmentation trees. So how it works? First, we should specify the name of our molecular, and of course we need to specify structure and MSMS spectrum. If we press check input data, we will see our structure and MSMS spectrum in the conventional view. So now we need to create ion. So how we can create ion? We need to add charge to some place of molecular. For this case, we need to show molecules with atoms IDs, numbers of atoms, and IDs of atoms, and we need to specify the number of atom to which we are adding proton. For example, in this case, we are adding proton to atom with ID 15. This is the nitrogen 15 here, and we are pressing create protonated molecule, and you can see now here that this atom is protonated. It's possible to protonate some other atom. For example, we can protonate oxygen atom. Remember the previous video in which I was talking about protomers. Protomers, they are gas phase isomers, which differ only by site of protonation. And during electrospirionization, such protomers can be formed, and in collision cell, we have absolutely no way to separate protomers. We are getting them simultaneously, fragments simultaneously, and we observe spectra. We observe integral spectrum produced by fragmentation of all possible protomers, but it is known that MSMS spectra of different protomers are different, and there is only one way to separate them, is using ion mobility spectrometry. So this is why we are adding this option to PyFragMS, option to specifically tell to the software the ID of atoms that you wish to protonate. It is also possible to deprotonate molecular. For example, if we would like to say remove hydrogen from carbon with ID 13, this is just a demonstration. Of course, it's not physically possible, but to show you how it can be done using PyFragMS, we should put minus here, and you can see that carbon is deprotonated. If we do not specify any number here, the molecule will be just the same. So it's like radical ion. So let's protonate nitrogen 15, and what is here? Set ID of atom with labile hydrogens only for HD exchange input. If, for example, we would, I will show you this later. Here we can specify not only regular MSMS spectrum for non-modified compound. We can specify here isotopes. For example, we can specify here hydrogen isotope or oxygen isotope or oxygen isotope. And if we are specifying here deuterium, of course we need to specify functional groups which with labile hydrogens. We need to specifically tell to the software which groups we are protonating. In which groups hydrogen deuterium exchange occurs. For example, now we are protonating nitrogen with ID 15, and if it would be hydrogen deuterium exchange experiment, we will need to specify this number of this atom to tell software to replace this hydrogen for deuterium. Maybe it's not shown good, difficult to see. Yeah, here. Now, if you look here, you can see that ionizing hydrogen, which was attached to oxygen with ID 5, now it's deuterium. You can see two index here. Okay, but now let's forget about deuterium. Let's once again return to protonating hydrogen. So now we have created protonated molecule. We have input MSMS spectra, and we can start building fragmentation tree. Just to press create fragmentation tree. Here in this field, we can specify the number of circles, the depth of fragmentation tree. What is depth of fragmentation tree? Basically, you can understand the concept of depth here. The depth of fragmentation tree 1 would be just here, the first layer, and if we just a single fragmentation event, and for example depth 2, we will consider two fragmentation events. So fragment ions will also produce fragment ions. So now the fragmentation tree is computed. Here you can see what kind of formulas were found, were used for building fragmentation tree, and of course to see what we have calculated, we need to press button run graph with. We are using graph with software for calculation of fragmentation tree. Now the tree is calculated here. For better visualization, it's possible to download image. So it's here. We had initially a molecule of this structure protonated here, and to produce MOVZ 233, we need to fragment it here, and you can see formation of fragment ion here. And for example, for forming MOVZ 149, we can fragment it here. For forming 126, it should be fragmentation once again here, but charge will be here, and so on. So this how it works. There is interesting observation which can be done regarding protomers. Let's consider these two fragments. Here you can pay attention to such labels: theoretical formula and experimental formula. And here, theoretical formula and experimental formula. What's theoretical formula? Theoretical formula would be the molecular formula of this fragment. If you just take molecular, break this bond, and calculate molecular formula. What's experimental formula? Experimental formula is a formula from input, which we are trying to use for creation of they are different. You can see that sometimes they are different in the number of hydrogens. Here 17 hydrogens and here 16 hydrogens. Why? Because in PyFragMS it is allowed that theoretical formula, say formula of this fragment, could differ from real experimental formula by one hydrogen. Why? This is to allow for possible formation of protomers and to hydrogen scrambling, hydrogen migration, because hydrogen is labile atom. It could move between fragments, and sometimes it happens. So this is why sometimes those formulas do not exactly coincide. And what is important? Important is that by accurate considering such formulas, we can try to distinguish between different protomers. So, for example, let's see, for example, on this fragment. Now, it will be better if I just show you the fragmentation when we say protonating oxygen. Okay, so now it's oxygen is protonating here. So let's have a look on yes, let's have a look on this. On these two fragments. If if oxygen is protonated, then you can see that theoretical and experimental formula do not coincide. But if nitrogen is protonated, then theoretical and experimental formula do coincide. So we can say that if oxygen is protonated, then this fragmentation pathway is wrong. And if, say, oxygen is protonated oxygen, then, for example, for this fragment, theoretical and experimental formula are the same. So this fragmentation pathway is correct. And here you can say that if nitrogen is protonated, they are different. Those formulas are different. How it could be verified? It could be verified using, of course, hydrogen results of hydrogen-deuterium exchange experiments. For example, if this fragment will not carry deuterium, it means that it is formed when ionization occurs here. Otherwise, it would carry deuterium. And if we go to database, to our database, and for this molecular, we can check the inclusion of deuterium in the fragmentation spectra. We can see that this fragment is indeed does not carry deuterium. So it means that if ionization occurs here, then this fragmentation pathway is possible, and this fragmentation pathway is not possible. Let me demonstrate how PyFragMS can be used for automatically for performing such results computation for performing such experiments automatically. Let's paste it here, and for our convenience, I just remove some data which are not which were not used here, just for simplicity. Yep. So now we are inserting spectra after hydrogen deuterium exchange. So you can see the position of deuterium in spectra. Once again, show atoms with ID. Let's protonate oxygen, and here we should specify that we are it's not protonated, it's deuterated. And if we create fragmentation tree, you see the considerable decrease of compounds, of fragments. Why the number of fragments was decreased? Because now we are explicitly using information from the hydrogen deuterium exchange experiments. Because, for example, this ion, we know that this fragment in real experiment does not carry deuterium, so software also uses this information, and we can see that if ionization occurs here, then only such fragmentation pathways are possible. If we look here, we can see that here this structure corresponds to MOVZ 234, and those two structures corresponds to same MOVZ. But if we look on the structure of those ions from general physical knowledge, we of course should say that the probability of such fragmentation is considerably low compared to this one. So only these two fragmentation pathways are possible. In PyFragMS, it's possible to remove some nodes which are not desirable. You can see ID of node here, 3 and 4, and they could be removed because they are unlikely. So you see, and if we just let's download image, yeah. And if we protonate, say, nitrogen, do not forget to deteriorate it. Now nitrogen is protonated. Let's calculate fragmentation tree. Yeah. And let's, oh no, no, I forgot. And let's download image. So what do we have here? Pay attention. Deterioration here and deterioration here. And if protonation ionization occurs here on this side, then only such fragmentation pathways are possible. And here, if ionization occurs here at nitrogen, then you can check which fragmentation pathways are possible. This one, forming this sign, this one, and those are unlikely pathways because you see it requires breaking of two bonds. So this is a demonstration how using PyFragMS it is possible to reveal, to investigate real fragmentation pathways and how it can be used for creating a data set of correct fragmentation pathways. That is what we are doing right now. It is also possible to use not only deuterium, it's possible to use oxygen 18 information and so on. So this how it works. It is possible to download not only image, it's also possible to download file for graph with figures, so you can build graph locally on your computer, and it's also possible to download fragmentation graph in pickle Python dump file. So you can download it, then load in your own code, and inspect it, modify, and do what you want with it. It's also possible to have this information. So this is how this block for creation of fragmentation tree works. And I just show you that it's also possible to calculate fragmentation trees for higher number of for high depths, for high number of circles. For example, for 2 circles, the calculation will take more time, maybe several minutes. So let's wait and see what we will get. Using PyFragMS, it will be possible to understand the real fragmentation pathways, and if we will know real fragmentation pathways, maybe it will be possible not only to create a better software for prediction of MSMS spectra in silicon. So we think that this is really important for increasing our knowledge and our abilities in mass spectrometry. Now, okay, 3 is calculated. You see, it's now a little bit more complicated. And you see that this is our precursor ion, possible first step of fragmentation, and for example, such ions could produce fragments, which could also produce other fragments. So, for example, you can see that fragment with MOZ 175 could be formed only as two consecutive fragmentation events, like here. So first of all, this ion is fragmented. Is fragmented to give this ion here, and only then fragmentation occurs somewhere here. And using oxygen deuterium, using for example oxygen exchange, it is possible to check which oxygen is losing in the following fragmentation events. So now